So you do each of those minus the mean. And we had from the beginning that our mean was 56, so you do each of those minus 56. So I try to give you some nice numbers so you don't have to deal with all the decimals. What should this add up to if you've done it correctly? Yeah, that's a quick check. That column should add to 0. And then you do each of those squared. Okay, 25, 16, 9, 4, 0, 4, 4, 4, 9, 25. All right, grab your formula sheet. So really, everything you have to do is on the formula sheet, but you have to know how to read that sheet and use those formulas. So for standard deviation, this is a sample I told you, and it says f the sum of x sub I minus x bar squared divided by n minus 1. So we have a square root. We add up all of these, and we get 100 divided by n minus 1. So how many points were there?
10.
So 10 minus 1 is 9. So then we just put that in our calculator. Don't forget the square root. On our last quiz, I think that was a pretty common thing, dropping the square root or dividing by the wrong piece. So it's the square root of 100 divided by 9, and we get 3.333. And then I, variance, if you look at your formula sheet, is s squared, so it's just the number we got squared. So that's where I got my other numbers. Is that okay? Do you guys all see on the formula sheet why we have to have that square root? Okay. Let's go to the second page. D. Lower fence, negative 0.14. Upper fence, 0.22. E. The outlier is 0.29. 3A is 68%. B, 88.89%. 4, 80.6%. 5, geography had a z-score of negative 1.2. Math was negative 1.5, so geography was better. Number 6, if it's bell-shaped, you want the mean. If it's skewed, you want the median. Number 7, if it's bell-shaped, you want standard deviation. If it's skewed, you want the interquartile range. What do we need to talk about on that page? 4. Okay. All right. So we have our test scores, project score, and homework score. Each test is worth 20%. So what do I need to do here? So the first test times 20%, you could do 20, you could do 0.2. I'll explain in a second what the difference is. Okay, so either way is fine. The next test was 83, and that also had a weight of 20, or if you're using 0.2s. Next test was 91 with a weight of 20. The term project was 88, and how much is the project worth? 25. So 25 or 0.25 if you did the decimals. Homework is 76, and how much is homework worth? Okay, so 0.15, or I did minus whole percent, so 15. Divided by. Okay. We have to add up these weights. So if you set up like I did, this adds up to 100. If you did the decimals, when you add all those up, what did it come out to? 1. So if you did it this way, you divide by 100. The other way, you divide by 1. Okay, so same thing. So now we work this out. So 62 times 20, 83. And so that equals 80.6%.
And on number 5, rise of geography.
Okay, let's look at number 5. So we have two different scores. Geography and math. In geography, we know their score was 62. And on the math, their score was 261. Geography, the mean was 80. Standard deviation 15. Math, mean is 300. Standard deviation of 26. So we have to find the z-score for each. So if you look on your formula sheet, z is x minus the mean divided by standard deviation. So for geography, we would have 62 minus 80 divided by 15. So if we work that out, we get negative 1.2. Right, so for this one, your score minus the mean divided by standard deviation, and that one gave us negative 1.5. Alright, are we okay here? What do those negatives tell me? They're below average. So here is the mean, or average. In geography, I had 1.2 standard deviations below, so my geography score is here. And in math, I was 1.5 standard deviations below. So my math is even more negative, so it was even lower than that. So in which one did we do better? Geography. We're below average in both, but we are less below average in geography. If those had both been positives, which one would have been the better score? The 1.5, because they would have been above average, so the higher above average you are, the better the score. Does that make sense? Anything else on this page? Number 8. Let's talk about that one together. I feel like maybe the next couple pages we should talk about together. I feel like we did better on the earlier stuff and maybe haven't had as much practice with the later stuff. So what should I do to compare these two cars? Okay, so we can put them in our calculator and we can look at the mean and standard deviation for each. So what do we get for the mean of the first car? Standard deviation. 1.797. The second car had a mean of 229.2 and a standard deviation of 51.813. So I'm asking you which car would be a better investment. And we kind of have to look at this and make some determination. Looking at the mean, which one is better? Car 2, by a little bit. Okay, this was how many miles they can drive on 10 gallons of gas. So we're seeing less than 6 miles difference. Is that significant for 10 gallons of gas? Not really. Okay, that's less than 1 mile per gallon difference. What do you notice when you look at the standard deviations? Yeah. The first car has a standard deviation that's less than half of the second. What does standard deviation tell us? It's more regular, more consistent. It tells us how spread out the data is. So we see the second car has a really high standard deviation, which means its values are really spread out. Sometimes my mileage is excellent, and sometimes it's horrible. The average is slightly higher than the first car, but I know that sometimes I'm not going to be anywhere close to that. And sometimes it'll be way better. So which of these two cars would you pick? Probably car 1. So something like this, you would have to be able to justify it. So we might say that even though car 2 has slightly better mileage, car 1 is significantly more consistent, so it would be the better option for us to go with. Is that okay? So number 9, we were looking at all this. I did not specify that you had to do a scatter plot by hand, so you could have used your calculator. You're kind of getting something generally like that. So what kind of relationship would that be? A negative linear relation. Okay, were you able to find the correlation coefficient on your calculator? So it's negative 0.9805. Everybody has that? So I want to know if that's linear. All right. If I just look at that, does it seem like it's probably linear? Yes. But if I wanted you to justify to me why you're saying it's linear, we really need to use our table for that. And I even told you, use table 2 to support your answer. So if we look at table 2, we're looking for our critical value. How many points did we have? 7 points. So everybody look at table 2 on your formula sheet. When our n is 7, what is the critical value? So remember, we said it was linear if the absolute value of r was bigger than the critical value. That's our guideline. So is the absolute value of negative 0.9805 bigger than 0.754? Yes, so it is linear. So on the test, you can expect me not just to say, is it linear or not, but I'm probably going to tell you, use that table. So I'm expecting you to jot down that critical value so I know that you looked at it, and you're looking is if the absolute value of r is bigger than that number. Coefficient of determination. How do we find that? R squared. If you forget, it's on your formula sheet. So r squared we can get a couple different ways. You could get it from looking at the calculator, the same green screen that told you r gave you the r squared. Or you could just take the r we have and square it. So you should get 0.9614. And interpret it. So that means write me a sentence. So if you are looking at your formula sheet, remember it tells us what a lot of things are. And it says the coefficient of determination, r squared, measures the proportion of total variation in the response as explained by the regression line. So this means 96.14% of the variation in our y value, which y was what in this problem? So 96.14% variation in the well-being index is explained by the regression line. that make sense? Did we get these right? Are you correcting it if you had a mistake? Make sure we all understand. Then I asked for the regression line on the calculator, which is the same screen that you've been staring at for r and r squared. So that was negative 0.0479x of 69.0296. Interpret the slope and y-intercept. Its slope is y over x. Y was the well-being index. What was x? X was our commute time in this problem. So what does the negative mean? So the well-being index decreases by 0.0479 for every minute of commute time. The y-intercept, what does that tell me? Y-intercept is when your x is 0, so if you have a 0-minute commute time, that is your well-being index. It's like our starting point, our threshold there. All right, part H, predict the well-being index of a 25-minute commute time. So what do you have to do? Plug 25 into your equation, and you should get 67.8321. So then, I asked for the residual. You forget, residual from your formula sheet is observed minus predicted. Observed is what actually happened. So look back up in your table. When we had a 25-minute commute time, the well-being index was 67.5. Minus predicted, what we expected to happen, was the value we just found. And if we subtract those, we get a negative 0.3321. Okay, so that means our observed value was just about 0.3 lower than the predicted value. All right, do you guys remember how to do the residual plot? Okay, so you have to run the linear regression first, and then you go into your stat plot. On the scatter plot, you change your y to residuals, and you should have gotten something that looked kind of like this. Remember, on a residual plot, we want no pattern. We're looking at outliers, patterns, or constant error variance. So if I'm looking, does this like widen as time goes on or anything? No. Does it look like a parabola or anything weird like that? Any obvious outliers? So the residual plot doesn't have any issues, so that means a linear model is appropriate. There were no rules violated. All right. So number 10, I had you go back to that problem and remove one of your ordered pairs. And when you do that and get the new line, it's a negative 0.0483x plus 69.0881. And so I'm asking if it's influential. Now, influential, it's kind of like when we talk about skewed. It's not always obvious. You know, we can tell if something is very skewed. We can tell if it's perfectly bell-shaped. In this, we can tell if a line is way different than another one. When there's not a huge difference, it is kind of up for interpretation to some extent. But if we look at this, let's compare it to the other line. You could graph them. We could look at the equations. So the original slope was negative 0.0479, negative 0.0483. Is that much difference? No. Y-intercept 69.088, 69.0296. So those are all pretty close to one another. So this would really not be influential. The slope and y-intercept had minimal change by removing it. Is that okay? All right, number 11, the one everybody wants to go over for sure. All right, so I will probably have you do one of these by hand. And it would probably be pretty similar to this in that a small set of data, because it is a lot of calculations, so it would not be very many points. And I would have you use your calculator to get the original values. So you need the mean and standard deviation for each variable. How do we get those? Calculator. Put x is in L1, y is in L2, stat, calculate two variable statistics. And what did you get for x bar? Standard deviation. 2.07364. Y bar. 8.6. And standard deviation. 4.2 and 9. Alright, is everybody okay with those? So then we have to create a table. So the first column, we are going to list all of our ordered pairs there, so we can kind of keep everything straight. On your test, I will have the headings set up for you already, just to kind of help. So I will tell you this is your ordered pair, X, Y. Then next, we have to do the x minus x bar divided by standard deviation. Then we do the same thing for y's. And then we multiply those. So I will have those headings on there already, kind of help you remember and organize what you need to be showing me. So our ordered pairs, we had 3, 4, 4, 6, 5, 7, 7, 12, and 8, 14. All right. Grab your calculator. We are doing my x. So the first x was 3 minus the mean of the x, 5.4, divided by standard deviation of x, 2.0736. And I'm just going to hit second enter and change my x values all the way down. So the next x value was 4. Next one was 5. Seven. And 8. Okay, everybody know where I got those numbers? Same setup, but now we're doing our y's. We'll use the mean of the y, standard deviation of y, and all of these y values to calculate. So I will have 4 minus 8.6 divided by 4.219. change, do second enter and change my y's. And then what do we do to get the final column? Multiply those two numbers together. So I have filled out my entire table. That's right there is a lot of points. So just take that time, make sure your numbers are accurate. Then look at your formula sheet. So we are finding the correlation coefficient. So the first bullet under chapter 4, it says R equals. What does that funny looking E thing mean? Sum. So I have to add up all of these numbers. So that gives me, oops. .9778 divided by n minus 1. So n is the number of ordered pairs. We had 5 ordered pairs, so we divide by 4. So I get a correlation coefficient of 0.9945. Actually, it's 0.445, but you could round. Okay. Is that one okay? How could you double check this if you wanted to? Calculator. You could run the linear regression. You already have the data entered. And just compare. There is potential that it might be slightly different because we rounded a lot, but they should be very close to one another. All right, so then it says use these to write the equation for the least squares regression line by hand. So you can use your calculator to check it, but if I ask you to do it by hand, that means you better show me the work for how we're doing it by hand. So look at our formula sheet. It says the least squares regression line is y hat equals b sub 1 x plus b sub 0. And it tells us b sub 1 is r times standard deviation y divided by standard deviation in x. And b sub 0 is y bar minus b sub 1 x bar. So all of this is given to us. We just have to use it. So to find my b sub 1, my r, 0.9945, times standard deviation in y, 4.219, divided by standard deviation in x, 2.0736. The slope is 2.0234. If you had kept all 5 digits on your R value, you would have had 2.0233. So just rounding, so make sure you have enough work and know where it came from. So currently, I have this much. Then I need my y-intercept. So, we go here. The y-intercept is the mean of y, which was 8.6, minus the number we just got, times the mean of x, which was 5.4. We get negative 2.3264. If you had kept that original r value, if you hadn't rounded it, then your slope would have been different by just a bit. This y-intercept would have came out to be 2.3258. So it's kind of a spiraling. The more we round, it continuously throws off numbers. I just have to see the work to know why you got the answers you got. Okay? You can compare that to your calculator. We know it probably won't be an exact fit, but they should be very close to one another. Is that okay? Did that help? Lots of calculations. The math isn't so much hard, it's just tedious. Lots of numbers. Right, number 12 told us the linear correlation between violent crime and the percentage of the population with a cell phone is negative 0.918. So is that a pretty strong correlation coefficient? Yeah. Okay, so does that mean that the increasing percentage of the population with a cell phone would decrease the crime rate? No. Why?
You don't know which axis.
Hmm?
You don't know which axis.
Okay. Yep. So we found that there's a relationship, right? A decreasing one seems pretty strong. But knowing there's a relationship, do we know that one thing causes the other? No. Didn't we kind of look at an example, I feel like in class where I did, compared crime rates and ice cream sales. And we said when crime rates are going up, ice cream sales go up. And we know those things are totally unrelated. But what did they have in common? The heat. Okay, so just because there's a relationship doesn't mean one thing's causing the other. There might be an outside variable that's influencing this. And what do we call those outside variables that we may not account for? Lurking variable. There could be a lurking variable, something we didn't consider that is impacting both of these things. All right, the last one. So there'll probably be a few multiple choice questions on this test, kind of a lot of the interpretation stuff, just because it's hard to throw those into all the problems. So this would be a good type of multiple choice question, looking at these residual plots, which one's a good model or what's wrong with them. So if I look at the first one, is that a good residual plot?
Yes.
Yes, there's nothing wrong with that. So that would indicate a good linear relationship. What about B?
No.
There's a pattern. So that one is not a good model because there is a pattern. C, bless you. Right, that one is getting more and more spread out as time goes on, so it's violating constant error variance. So it is not a good model. D, what do we see?
Pattern and outlier.
Yeah, there's a pattern and we have an outlier there. So there's several things wrong with that. All right. What questions do you have that I have not gone over to this point? All right, let's say I said, So we have distribution. Mean is 60, standard deviation is 6. If we don't know anything about the shape of the data, what percent should fall between 48 and 72? What am I doing here? Chevy Chevs. If you don't know the shape, you have to use Chevy Chevs. So remember, this means my center is at 60. So one standard deviation would go 6 below, so 54, and 6 above, which is 66. I did not. Oh, sorry, I thought I was asking a different question. But. All right, so 2 standard deviations. We would have to do 48 and 72. So that means 2 standard deviations. Since we don't know the shape, we have to use Chevy Chev. So 1 minus 1 over k squared. What is k?
2.
And what's that give me? 0.75. So that means Chevy Chev's rule tells me 75% of my points should fall between those 2 numbers. All right, if I know my data is bell-shaped, what rule do we use if it's bell-shaped? Empirical rule. Okay, 42 and 78. So I'm not there yet. I have to go another standard deviation. So if I keep adding and subtracting 6, this would take me down to 42 and 78. So I'm talking about 3 standard deviations. So according to the empirical rule, how much of the data should fall within 3 standard deviations?
99.7.
So empirical rule if it's bell-shaped, Chevy Chevs if it's not. That's okay with everybody? You know how to find quartiles and interpret those if I ask you to write a sentence? Use a calculator to find them, yep. First quartile means 25% of the data is less than or equal to that number, and so forth. How do we find outliers? What do we have to calculate? Upper and lower fence, good. We talked all about the correlation coefficient. Okay, if my data is bell-shaped, what is the best measure of center? The mean. If it is skewed, the median. If my data is symmetric, what is the best measure of dispersion? Standard deviation. If it's skewed, interquartile range. Out of all these things that we found, mean, median, mode, interquartile range, standard deviation, range, what's the only one that could have more than one answer? The mode. We could have multiple modes. What is the mode? The number that gets repeated the most. So we could have multiple modes. Everything else, we should only get one answer. How do you decide if a point is influential or not? You can look at comparing like the R squares. You can look at the regression line and see, any point, if we take it away, we would expect a small shift in our line. It's influential if we have a big shift. When you're comparing standard deviations, is a bigger or smaller standard deviation better? Smaller standard deviation is better. It means it's more consistent. Anything else? I really feel like you guys are ready. I feel like you know this. I'm going to take it right now. Just stay in here next hour and get it over with.
I'm gonna skip weights. Don't tempt me.
Woo.